Okay, so this is a digression lecture for this week 6. We actually have talked about pointers in this week, but I actually wanted to put this video before the week, but it got a bit delayed. But here it is. So this video is about, just to give you a brief idea of what processes are and what exactly is multi-programming. So this will just give you an idea of how things happen in the background when you run a program. So let's just discuss what processes are. If you are on a Linux system or a Mac system, you'll probably have a command called top, okay, on your terminal. If you run that command, you will be able to see the list of all the currently running processes on your system. Okay, this is something that you can see. This whole window is actually trying to show you the currently running processes on your system. This is just a screenshot, and out of all these information that you could see here, probably the only one that we usually look at are the CPU percentages and the memory that a particular process is using, right? So you can see some of the processes that are running on my system, like Google Chrome or VirtualBox. Okay, so usually this is one way in which you can have a look at the processes. And just to give you a brief idea what processes are, you probably already know this term, but processes are units of execution that your operating system executes. Okay, for the operating system, even a hello world program is a distinct process, right? So whenever you run a hello world program, it turns into a process. This is the idea. So basically, a program is a compiled time entity, something that you write, and then when you execute it, it turns into a process. And this whole thing, no, the process thing, operating system actually has a fixed template for creating, executing, and ending processes, right? So you remember that we discussed that return value from the main. So that is a part of the ending of the process part. And similarly, there is a whole cycle. Okay, we call it the process life cycle. So basically, the operating system, in the beginning it creates your process. This is basically it involves putting whatever is necessary for your program to run in the main memory. Okay, and once everything is ready, okay, we call that the state. The process is now in a ready state. It is not yet executing, but it is now in the ready state. Then what happens is there is a kind of queue. Okay, in a queue, it is maintained that these are the processes which can now be executed. They are ready to be executed. So based on your operating system's scheduling policies, your process, okay, and let us, whenever I'm saying process, just assume that it is a program that you wrote, and let us say you did gcc something.c, and now you have just done dot slash a dot out. So that a dot out is going to turn up into a process. So at one point of time, your program will start executing. Okay, then it is called as the state of the process has turned into running. Now sometimes, because of one reason or the other, for example, there could be an IO request, as in, let us say you have a scanf statement. So your process cannot execute anymore until the input output is finished. um, or there might be some other reasons, like we haven't actually done uh, so much programming, but there are other ways as well in which a particular process can be blocked. But the idea is that there can be some reasons because of which your process might actually temporarily, okay, not permanently, but temporarily cease to execute. One example that I gave is, let us say you have a scanf statement. So until the input has been given, your program basically halts at that point. So essentially, um, this state is called as the blocked state of your process. And there are some categorizations where they consider the new and terminated states as two different states. So this is not really a very standard terminology here. Usually it's just these three: ready, running, and blocked. That is what people use. Some people also say that new and terminated are also two different states in which a process goes through. So this is the more important part that I want you guys to understand, that whenever a process gets created by the operating system, um, within the memory, right, within the main memory, some space is allocated. This is what I was telling you when we were discussing pointers, that some space is allocated, and that space looks something like this, right? I mean, it's a it's a highly simplified view of that process. You know, there are many more things that I should have shown, but just to give you a brief idea that there is some memory here. With this memory is essentially the memory that is used to store your variables. Okay. So as of now, this is all you need to know, that out of this complete memory, some memory is dedicated to store the code, the actual instructions of your program. And by the way, these instructions are not really Java or C code. This is somewhat similar to what we actually saw in week 0. Okay, so this is kind of assembly language code or machine code. So there is some part of this whole memory that was allocated, there the code resides. And then the other part of the memory, I have actually written memory, I should have written memory for variables here, something like this. So basically, this memory keeps all your variables and constants that your code requires. And there are different types of memories. I mean, you must have heard some of your peers talking about things like heap and stack. I'm not actually going into the details of that, but basically there is some space within the memory space of your process, where your variables are allocated. And then we already know what program counter is. So program counter essentially starts from the first instruction in the code area, and then it just keeps on going down, right? We have discussed what a program counter is in week 0. If you don't remember, you can probably go back and look at those lectures. So one more term that I want to discuss is multitasking. Now, in the beginning, I showed you the picture of that top command, right? And in the top command, you could see that there were multiple processes that it was showing as active. Now, what really happens is that most of the operating systems today, I think almost all the operating systems today, they do this thing known as multitasking, where what they do is they keep a number of processes alive simultaneously. When I say alive, it essentially means that these processes have some space allocated to them in the main memory, the RAM. And what happens is, at any particular point of time, the operating system picks any one of them. And by the way, whomsoever are there in the RAM, they're usually in the ready state. It's not necessary that they are in the ready state. We talked about those states, right? But yeah, they are either ready or blocked. Okay, blocked means that they are waiting for some event like an input output, or they are simply ready, they are just wanting to be executed. So what happens is, this operating system picks up one of the processes and executes it for some amount of time. This amount of time is also known as a quantum. Okay, so these are short periods of time for which your operating system will allow a particular process to execute. And then once this time expires, if the process has not yet finished, it will actually cease to execute. So it will be stopped from executing, and it will be put back into the ready state. um, and what happens is, this is essentially how your operating system is able to um, emulate it is able to show as if multiple processes are running simultaneously, because this switch between one process and another, it happens so fast that for a naked eye it might seem as if multiple processes are running simultaneously. But in reality, if you have one CPU, one core, then only one process can actually execute at any particular point of time, right? And this is where the value of your program counter becomes so crucial, because if I actually stop a particular process from executing in the middle, all I have to do is save some state. Okay, the state of the process when it was executing, and the most important part of that state is your program counter. So if I know exactly where was the program counter when I stopped this process, when I give it the second quantum, it will be able to execute from the same point. So it's something like this. Let us say your program requires about 100 milliseconds of execution time, and the quantum that is decided by the operating system is only, let's say, 30 milliseconds or so, then your program will need 4 quantums to finish, right? I mean, it will get 30 milliseconds of time to execute. So some of the instructions of your program will be executed, and then it will be put in the ready state. Then in a round robin fashion, it will get 30 milliseconds again, then again, and then finally in the fourth 30 millisecond quantum, your process will finish off. So this is basically the idea. This is just another way to show the same thing, that we start by there are 3 processes here. They are all ready to be executed. The first quantum goes to process 1. After the quantum expires, it becomes ready again. Then this quantum goes to process 2. The others are currently waiting in the ready state. Then the third one gets um, the process 3 gets the quantum, but something happens. Let us say there is an IO request at this point of time. So then the CPU goes to, in the round robin fashion, it probably goes to process 1 again. This is not necessary that it happens exactly like this. It is more uh, to just show you, how these things happen. um, so basically, it might go back to process 1 or some other process. The idea is that when a process gets blocked because of some IO, it cannot access the CPU as long as that the reason for blockage is over. So for example, the scanf statement now has executed, and you have a value, and you can now start executing again. So then this is just an idea of how multitasking happens in most of the modern day systems. There is a reference here. This is a book, actually. It's a very advanced book, so you don't actually have to read all of it. There is a section there, 10.1. So if you can get hold of this book, try to read the section 10.1. It might give you some more details. Okay, thank you.